Hi everyone, today we will study Jacobi fields on complete Riemannian manifolds. They allow us to study families of geodesics traveling together. We know that in positive and negative curvature, these families behave very differently, and that will be reflected in the Jacobi fields. To avoid dealing with technical issues, we will assume that the Riemannian manifolds are connected and complete. We will start today with some definitions. If we have a curve gamma on a manifold, a smooth map phi from the rectangle minus epsilon epsilon times AB to M is called a variation around gamma if phi of 0t equals gamma of t for all t. The derivative of phi with respect to s at 0t is a vector field along gamma, which we call the vector field associated to the variation. This vector field represents how separated these curves are and was used in the lesson about curvature. When for each s, the curve phi of st is a geodesic, we say that phi is a variation by geodesics. We will show that the vector fields associated to such variations satisfy a nice equation called the Jacobi equation. Let j of t be the vector field partial phi partial s. When we take the second covariant derivative of j, we get this expression involving the curvature operator. In the lesson about minimizing curves, we showed that by the torsion-free condition of the Levi-Civita connection, dt partial phi partial s equals ds partial phi partial t. In the lesson about curvature, we learned that the commutator of the covariant derivatives can be written in terms of the curvature, meaning that this expression equals ds dt partial phi partial t plus a curvature term. We are assuming that the variation is by geodesics, so the second derivatives of phi with respect to t are 0, leaving only the curvature term. Along the geodesic, partial phi partial t is gamma prime and partial phi partial s is j. This is what we call the Jacobi equation. We will say that a vector field along a geodesic is a Jacobi field if it satisfies this equation. What we will show next is that a vector field v along a geodesic gamma is a Jacobi field if and only if there is a variation by geodesics around gamma with v as its associated vector field. We already showed one implication and now we prove the other one. Take E1, E2, E3, a basis of parallel vector fields along gamma. We will use this basis to rewrite the Jacobi equation. When we write the curvature r gamma prime ei gamma prime in this basis, we get coefficients we call aik. We can then write any vector field j as jk ek and write r gamma prime j gamma prime in the basis e1, e2, e3. Because the vector fields ek are parallel, when we take the covariant derivatives of j, we only differentiate the coefficients. We will use dots to denote the derivatives with respect to time. Then the Jacobi equation becomes jk double dot equals aikji. This is a linear second order ODE, meaning that given initial conditions, there is a unique solution and the solution depends linearly on the initial conditions. Since the equation is second order, the initial conditions are the values of j and dtj at time 0. Now assume that the vector field v satisfies the Jacobi equation. We will construct a variation by geodesics phi with v as its associated vector field. Let alpha be a curve with initial velocity v of 0. Also construct a vector field zd along alpha with zd of 0 equal to gamma prime at 0 and dsd at 0 equal to dtv at 0. With this, we can construct the variation phi given by exp at alpha of s of t times zd of s. Denote partial phi partial s by j. Since the variation is by geodesics, j is also a Jacobi field, so all we need to show is that j and v have the same initial conditions. When we take partial phi partial s at 0, 0, it becomes the derivative with respect to s of alpha of s, which we chose to be v of 0. On the other hand, by the torsion-free condition, dtj is ds partial phi partial t. When t equals 0, this is the covariant derivative of zd with respect to s, which we chose to be dtv of 0. This shows that j and v have the same initial conditions, so they agree everywhere. This finishes the proof of the proposition. Using Jacobi fields, we can understand much better the exponential map. Pick a point P and a vector v tangent at P. The differential of xp at v is going to be given by Jacobi fields along gamma v. For w in TPM, dvxp of w is going to be given by j of 1, where j is the Jacobi field along gamma v with j of 0 equal to 0 and dtj of 0 equal to w. This is going to be very simple. We will work with the same variation we used to prove the Gauss lemma a couple of lessons ago. When t is 0, phi is constant, so partial phi partial s at 0 is 0. Also, dt partial phi partial s is ds partial phi partial t, which is the covariant derivative of v plus sw. This means that j is the vector field associated to this variation. On the other hand, by the definition of differential, j of 1 is precisely dvxp of w. Using Jacobi fields, we can prove the following theorem, which is the main step in the proof of the Cartan-Hadamard theorem. It is going to be our first approach to the field of comparison geometry, where curvature bounds provide global geometric information. If we have a complete Riemannian manifold M with non-positive sectional curvature, then for any tangent vectors v and w in TPM, the differential at p of the exponential map at p sends w to a vector at least as long as w. In other words, the differential of the exponential map cannot decrease the length of any vector. Another way to interpret this is that if we have a curve on the tangent plane, when we apply the exponential map to it, the length of the curve can only increase. Before we prove the theorem, we need a couple of lemmas. The first one is valid in any Riemannian manifold. If we have a smooth curve alpha and a vector field v along alpha that is 0 at the initial point, then b minus a times the integral of the length of the covariant derivative of v squared is at least the final length of v squared. This will be a simple application of the Cauchy-Schwarz inequality. Let E1, E2, E3 be a basis of orthonormal vector fields along alpha. When we write v in these bases, the coefficients of the covariant derivative of v are just the derivatives of the coefficients of v. Then we rewrite v minus a as the integral of 1 and the length of dtv squared as the sum of the squares of its coefficients. We pull the sum out of the integral and apply the Cauchy-Schwarz inequality. By the fundamental theorem of calculus, this is nothing more than the length squared of v at time b. The second lemma only works on manifolds with non-positive sectional curvature. If we have a Jacobi field J, then dt dt jj is non-negative. To prove this, we substitute dt dt j using the Jacobi equation. Then this is Rm gamma prime j gamma prime j. By the symmetries of the curvature tensor, we can switch the last two entries and get a minus sign. Now there are two cases to consider. If gamma prime and j are linearly dependent, this is 0 by the symmetries of the curvature tensor. If they are linearly independent, this quantity is minus the sectional curvature of the two-dimensional plane they live in times the area of the parallelogram they span. In either case, this is greater or equal than 0. Now we are ready to prove the theorem. Take J, the Jacobi field along gamma v with initial conditions 0 and w. By the previous proposition, we know that dvxp of w is j of 1, so if we define f as the length of j of t squared over t squared times the length of w squared, we need to show that f of 1 is bigger or equal than 1. We will show that f tends to 1 as t goes to 0 and that f is non-decreasing. This will prove the theorem. To compute the limit, we use L'Hopital's rule. Both the numerator and denominator go to 0 again, so we apply L'Hopital's rule again. Using the initial conditions of j, we see that the limit is exactly 1. Now we show that f is non-decreasing. We first compute the derivative using the quotient rule and then simplify a little bit. The fraction at the beginning is non-negative, so we need to show that the stuff inside the parentheses is also non-negative. We focus on the first term. Recall that j of 0 is 0, so by the fundamental theorem of calculus, dtjj is the integral of its derivative. We expand this derivative and substitute in the derivative of f. The term dt dtjj is non-negative by lemma b. By lemma a, t times the integral of dtj squared is at least the norm of j squared, so f prime is not negative. This finishes the proof of the theorem. In a later lesson, we will use this result to prove the Cartan-Hadamard theorem. Thank you for watching and see you next time.